Now we are going to learn about the film deposition of the wafers using CVD, PVD, and any other knob. First, the CVD means that chemical vapor depositions, which means that we use chemical reactions and like doping or etchings. Like first we mass transport the reactant, and we after then we react, and then we remove the byproduct. CVD is also very similar, and then there is a PVD, physical vapor depositions. It's like depositing the films with the physical way using ion implantations or sputterings. First, in depositions means that applying the putting a thin film on the surface, and as I said, CVDs are chemically reactive. There is a lot of four variables, varieties of ways: low pressure CVDs, plasma enhanced CVDs, and metal organic CVDs, and ALDs. In this in these sessions, we will going to learn about the low pressures and plasma enhanced and ALDs. Next, the physical vapor diffusions, uh, which are the deposit with the physical rays, which means like ion implantations or ion millings using a gas phase plasmas, like thermal evaporations or e-beam evaporations and sputterings. There is a lot of applications in depositing thin films. We can deposition the metals and polysilicons or silicons or dielectric layers like ILD, interlayer depositions, or oxide, and surface passivations for the electrically isolating. Using the CVDs, we can like grow the films in two ways or three ways. First, the 2D layer by layer growth, also known as Frank van der Meyer way. It has a pros that it can evenly grow on the surface. However, the selectivities are very important. And then there is a 3D growth. It's like for example, these metals on silicon dioxide. When we deposit metals on the dielectrics, the metals cannot be grown like here layer by layers because the silicon silicon dioxide. First, there is seed. Seeds are deposited. After that, it spreads out by the diffusions. After all, forms like a island shape. And lastly, there is a mixed growth. The mixed growth are shape of the homogeneous. Some of these two ways, layer by layers, also 3D growth. First, there is a 2D layer by layer growth. After some point, the 3D growth also happens. And also using these film depositions, we can make the epitaxial growth, which means uh, formed by layers. Uh, it's very slow. Using this epitaxial growth, we use source and drain contact in FinFET because using this epitaxial growth, it can support high mobilities on the uh, growth plane. However, it is a very slow process, but it can be also mm, it can be growth with the two materials like silicon germanium or 3,5 materials and complex oxide. Mm, and then for the silicon dioxide, high K materials, we cannot grow high K materials on the silicon itself. So we use here for the SEM, scanning electron microscope. There is a white layers in here. This is silicon dioxide. After we deposit the silicon, uh, after we oxidate the silicon dioxide, we deposit high K materials, hafnium oxide, like high K materials, and then the metal layers. And there is very important parameters for depositing thin films, a step coverage. The step coverage means that the difference between the upper side, width of the upper side and lower side. Uh, if the if there is a trench, then if we want to deposit the trench with the oxide or some materials, we can define these conformers as the thickness of the every side is very even. We say this it's conformers. However, if the on the there is a bottleneck, then we can say it's non-conformers because it is not even every side. The effect of the step coverage is that we can for the gate all around MOSFETs, it cannot cover this under these nanowires because it has a low step coverage. So the below bottom side of the nanowires cannot be deposited evenly. Also, for the DRAMs like here, which needed for a high aspect ratios, if the bottlenecks happens and the capacitance between the side will not be even, so we cannot drive target capacitance for charge capacitors on the DRAMs. Also, there could be a void which are filled with the airs. We can use this poor step coverage as the good dielectric materials, like the we can use void as a material using the electrically isolations. Here is the examples. Like if we see this Intel's 14 nanometers process, there is a different colors. Here is the air gaps or void. It's the on the metal layers to prevent the electrically interference between interconnects. We they use these void, the air gaps, the low K materials to isolate electrically between these two lines. And here's the DRAMs. Using these DRAMs for the high aspect ratios structures, it is important to conformally deposit the oxide because uh, if the oxide are not non-conformers, then the here where these another electrode cannot be get deposited here because of the bottlenecks. Also, it can affect the capacitance of the charge capacitors. CVD process can be set in 3 steps, like as I said, etchings or lithographies or dopings. We first mass transport to the substrate a source gases, source materials, and then we react with the substrate, and then we remove the byproducts, gaseous products. Also, reaction rates are defined. Reaction rate are critically affected by the lowest velocity of these 3 steps. If any others steps are has lowest reaction rate, then the total reaction rate is limited to these lower steps. Like here, introduce the reactive gas, the mass transport, the active gas using the heat or plasma to give external energies like reactions. After reactions, we transport these byproducts. The CVD, the for the process of the CVDs has like four kind of steps. We can also deposit films in the atmosphere pressures using this nitrogen gas to use as an air curtain for removing any other particles from the outside. And then we input this reactant gas like metal gas, silicon gas, oxide gas, or something else. And then we activate using heaters. We use thermal energies. The advantage of this using atmosphere pressure reactors is that it is very simple. So the yield, as the yield are not yield, as long as yield is bad, but it can produce many wafer as possible. And then this PECVDs, which means pressure electric CVDs, which used in a vacuum state, and we make this plasma on the here, and using plasmas we use these energies to activate this reactant gas. and then we drain out. The PECVDs has a better conformability or step coverage because it uses vacuums, so it is very clean. So we can use on chamber types or batch types. And however, it can be there is an interference between the argon ions, like here for source of plasmas. So it can be problems for step coverage also. So for the extreme conformability, like extreme step coverage, we use low pressure CVDs. The lower pressure CVDs is that the pressure has a millithorth or 2 thorth. So it's very more vacuum state than the PECVDs. So using this vacuum, and we put the gas, and then it is like same for it uses thermal energies. So what is the advantage of the using LPCVDs is that there is almost no interference between the air and the wafers. It can be easily deposited, no, evenly deposited. So it is very extremely good step coverage. However, LPCVD has very high disadvantage is that this process uses a long time for depositing films, and also it is very hard to sustaining this very high vacuum state. So the cost gets higher. The APCVD, the atmospheric pressure, and the PECVDs, LPCVDs. So as I said, PECVD has uses a plasma, so it operates in lower temperatures and has good step coverage. However, it is not better than the LPCVD because of the interference between the plasma ions and the reactant gas. However, and then it also has a toxic byproduct, and then it is very expensive for using a plasma. And then the LPCVDs, the mean free path, like as I said, there is a no interference between the ions or any particles. So the diffusion coefficient also gets higher. Then it has better step coverage than the PECVDs. So also LPCVD has no form of damage because the PECVDs uses a plasma. So these plasma ions can hit the wafers and damage the wafers. However, LPCVD does not use this plasma, so it has no damages. However, it is a slow process. So slow process means the cost gets higher, and it uses also a thermal heaters. So it has high temperatures process. Here's the APCVDs are used in the 350 degrees Celsius to 1200. the LPCVDs are on the 550 to 600. The PCVDs are very low between them, like here low temp oxides, like high K materials. The ALDs, the atomic layer depositions, is that it is very conformers because it deposit film with the atoms atoms layer by layer. So uh, it is very conformers. Using these ILDs, we can deposit oxides, nitrates, metals, various. Uh, there is a very variety of materials. However, but the ALDs must have these precursor uh, precursors. Using these ILDs, we use ILDs for the depositing, like here, fins oxide, and the for the epitexture growth. And then the RMG process, the recess metal gates process. After we shape the fins, and we also deposit the gate, and then like spacers, and the after the we put spacers, then we growth the source strain. After we etch the fin, and then we growth the source strain epitexturally, and then we etch this dummy gate. The reason we use this RMG process is that at when we dope these dopants, we use summer energies, very high temperature summer energies, to drive in and activate the activate the dopant source. Anneals. The annealing process has a very high temperatures, so it can damage this high K oxide. For the before then, the LPCVD's PCVD process was the 300 to 400 degrees Celsius process. However, the ion implantations or gets higher, almost is 1200 Celsius degrees. So we should dope first before making these high K materials metal gate. So the RNG process is prevent for the damage to high K materials and for thermal budget. And then there is a PVDs, the physical process. PVD is similar like CVDs. However, it uses a source as a solid or liquid to evaporate, make a vapors, and then turn into gas phase, evaporate, and then for the transport and deposition stage, we use these physical ways like sputterings. First, evaporation. When we there is a crucibles for target materials, and then we heat it up using a tungsten heaters or something as the heat source, we make this, we change the phase of the target materials to gas, and then for the upper side, make the target materials deposited in the substrate in the natural way, just evaporate, and the target material stick into the substrate. However, this way has a disadvantage because these in the vessels are vacuum, so the metals can be stick to the in the vessels. So the vessels must be cleaned up regularly. The sticked the materials, target materials can be get out for time by time, so need to be cleaned. It also has shadowing issues, and then the step coverage issues. Those are following issues. And then for the E-beam PVDs, we use the electrical beam to which uses a magnetic field to rotate this beam 270 degrees. The tungsten filament makes the heat and the electron beam. So there is, for the heterotype depositions, we use a lot of sources like here, like cylinders. We rotate the cylinders and use this same way. The step coverage issues, are due to the shadowing effect. So because of this shadowing effect, now we use the sputtering. The sputtering uses ion hit, the argon ions hit the target materials, then the target materials are bounced off or evaporated, and then it can be hit to the substrate, so makes films. Using these sputterings can help using very conformal films, because evaporated materials are vectors isotropically. So here and here's like, so it can deposit. It has a good step coverage. However, sustaining this certain vapors pressures is very hard, so it is hard to control. The pulsed laser depositions is that like UVs, so it's very expensive to hard to make. It uses electrical optical systems. The PLD uses certain laser beams, and using laser beams, hit the target materials, and then the materials are evaporated, and they hit the substrate. It is very similar to the sputterings. However, it uses very high power pulse lasers, and it can very it has a very good step coverage, because in the sputterings, like similar to the PECVDs, it can be these argon ions can be interference for free pass of the target materials. So it can relatively lower step coverage than the PIDs. So in the PIDs uses a very high vacuum state, so there is no interference between the materials, and then it has a very good mean free pass. So it has a very extremely good step coverage, like LP CVDs. However, it is very slow process, and then the devices are very expensive, so we not use these PLD techniques. And then the molecular beam epitaxy. When we grow this source drain contact, we do not use only for the silicon materials, silicons. We use silicon, germaniums, like here. We can gradiate these forms, mixtures, like mixture of this silicon germanium compound. So for that, there is a certain crucibles wrapped with the coils. The coils heats up the materials and evaporates, and then these evaporated materials gets heated from the many side, so it has a very good method for the epitaxials on the single crystals. Basically, it is a thermal evaporation. However, it is very slow deposition rate, so it needed to be ultra high vacuum systems. So, as I said, this molecular beam epitaxy is used for the multi-layers or hetero type materials. The metallization process is the usually on the process that the end of the process, in the end of the process. First, the metal contact and the inter contact, these the lateral sides, the contact, there is a lot of layers between the layers on the semiconductors. We call the interconnect is that the contact between the same layers, like contact between the transistor and transistors, or line line by line, and then the contact between the vertical line, we call this via. Nowadays, there is a lot of levels or layers of the metal lines. The only process of the metallizations is like similar to the on the oxidations. We first after we make the transistor shape here, uses a mask on the nitrate and the local oxidation layers. Using those two layers, nitrate and the locos as a hard mask. Then we deposit the metals like aluminums deposit. So using these ways is like similar to the oxidations. There could be a like on the locus, there could be a bird's beak. So there is a metal locus and the another locus. So the effective areas for the transistors is here. So it is difficult for the scaling down, but it has a very simple process. It does not need any other litho or etch. So we nowadays we don't use the this process. So the metal shape would be like here. So there is a possibility for killer defect like here can be short, and then there is a leftover space is very large. And then nowadays we use a planar metallizations. We first make a transistor shape, and then we add another layers like oxide, the ILD, the interlayer deposit. Using interlayer deposit, we deposit oxide films, and then we planarize with the chemical mechanical polishings, and we etched through the contact like source drain gate, and then we deposit the metals on the side. When we deposit the metals, it should be very conformers to prevent the void in the contact. Using the conventional aluminums has various problems. First, the aluminum spikings. The aluminum has this aluminum consumes silicon easily, so it can penetrate silicons. So we call this aluminum spikings. Due to spikings, like here, let's say there is channels between the transistors. Those spikes makes this can cause this excess leakage. So because the aluminum has a source of the electrons because of metals, and also if we make this PMOS or PMOS, then the PN junction would be here. So there could be a junction short. So both effect, the short circuit junctions and the excess leakage causes a bad swing. So device performance on and off margin is bad. So it can make bad performance for the device. And then electro migrations. As we use the device a long term, then the aluminums can form the void, like aluminums can fall off, and due to this electron flow, electric field, high electric field or long-term exposures, then the aluminum atoms can be swept back, make a hillock. It can cause this it can cause the higher resistance and low mobilities. So to prevent these happenings, we use barrier methods. Like we first cover this silicone surface using a barrier metal, which are not, which are less consumes silicones, like 1% of silicones or aluminum copper alloys. The contact resistance is very important because as these gates length, as we diminish the as we minimize these gate lengths, it cannot help for the physical dimensions or device scaling down. So both gate length scaling and the gate pitch scalings should be accompanied. So for the gate pitch are minimized, then the let's say if there's two fins, then there is a contact here. So also the contact to gate space should be lowered. However, it has a very bad for the contact resistance because these resistance are defined as proportional to the area. So for parasitic resistance are very diminishing for the many knobs. However, this contact resistance between source strains are not diminishing relatively for any others, external more resistance, like something else. For the another problems is that ohmic contact. When we contact between these metal and semiconductors has there is another PN junctions on the transistors. We call these MS junctions. We use various methods for the metals work functions engineering, because the threshold voltage or voltage applied for a gate is formed with the flat-band voltage and the threshold voltage are defined as a flat-band voltage and gate voltage and surface potentials. So nowadays, because of the for the FinFET, because of dopant fluctuations, we cannot rarely regulate these surface potentials or voltage applied for the gate. The VG can be regulated with the high K materials. So now we use this regulating the flat band voltage. However, there is another problem, is that the work functions are saturated on the ferromene levels. Like for the ideal case, the aluminum's work functions is located here. So we would like to even these vacuum energy levels to prevent this another depletion areas, prevent the depletion areas or parasitic capacitance. So we try to engineer the work functions. However, the work functions are saturated in mm, the mid gap of the silicons. So we call this Fermi level pinning. So for the real case, there should be spikes or difference between the difference of potentials must exist. For the ohmic contact, we have to try to make deliver the carriers between metal to semiconductor or semiconductor to metals using field emissions, which means it uses quantum tunnelings. To do so, we need to heavily dope the source drain contact. There is a lot of good conductivities like silver, gold, like platinums. However, those materials are very expensive, so we do not use nowadays. Nowadays, we use coppers, but the coppers has a very uh, very high disadvantage is that the coppers cannot be etched, wet etched, dry etched. So for the wet etch, we rarely use on the front end of the line, which means transistor structures on the wafers. For the end of the metal layer is we call this back end of the line bears. So the front line we use these coppers. So however, the copper easily diffuses into silicons and it cannot be wedged using a dry edge. The reason why we don't use the wet edge, the wet edge is usually isotropic, so it has it cannot provide the high aspect ratio. So the when we use coppers, we have to use barrier materials for like tungstens or molybdenum or nickels. Those are very low conductivities. However, we should use for the devices performance, devices continuities for good lifespan. So nowadays, we also use silicide, which are compounds between metal and silicons. The silicide has very good materials for low resistance, and uh, uh, it does not diffuse into silicons, and it does not have electro migrations. And very important is that it can be dry etched. So, so it is very good process. To make silicide, we put a metal on the silicon, and then we anneal the metals or give energies or heat, laser or ions. So makes the silicide. The silicide process are very low process. So it has a very low thermal budget. So um, before at the if we deposit the high K materials or the dopant, then we have to after we uh, ion implant the dopant or oxide, then there is a we have to cure with the heat. So if we if we cure after the metallizations, then the silicide can be damaged. So we use this silicide process as last process as possible. And then there is a metal insulator semiconductor contact. Because of the here the in the MS junctions, the carriers go through the uses a tunneling effect. So using the source drain, if you dope the source drain very high concentrations, then the mobility would be go lower, so it can cause more contact resistance. However, using these uh, insulators, very thin insulators, we can make carriers assisted with the oxide uh, oxide energy gap, so it can be more easily transported carriers. So it causes lowering the contact resistance. Nowadays, we use tungstens on the via on the MOSFETs, because the aluminum or copper has a very bad step coverage, and it can make a void on here on the metal plug. So nowadays we do not use because this bad step coverage makes the void, and the void are void causes a defect for the mean free path because of the interference of the void. So now we use these tungstens because tungsten has an excellent step coverage and it can fill the gap evenly. So there is no void. However, the tungsten has a very high work function, so it has a high resistivities. So tungsten is used for the local interconnections or the plugs for the MOSFETs. Also, for the barrier metals, we use titanium nitrate or the titanium silicide. Those titanium nitrate and silicide has a very effective for blocking the diffusion on the silicons. The sheet resistance is that the for the when we metallize the device, the thickness are defined as a design rule, so we cannot control it. So the parameters, the resistivities and the thickness are formed together, so make these sheet resistors. The reason why we use the sheet resistance is that to calculate the total resistance of the metal lines, more easier way. And the electroplatings uses ionizations uh, to easily more metallized simple ways or easily cheap. So we first put a seed layers and then the deposit ILDs, and then we electroplate these coppers. The Damaxin process is that using these electroplatings. So nowadays we use a dual Damaxin process for mass product. In here, for the former Damaxin process is used for making of vias here for the each layers. However, the dual Damaxin layers are for the two layers at once. We use this Damaxin process on the barrels, the back end of the line, because after this fin or MOSFET shapes are shaped, these metal lines are very complicated, and it should be not be the total summer budget is very low because of the high K materials or the silicide. So after these ion implementations of the high K materials, ALD of high K materials and the silicide, so after then we make these metal layers. So the SAC process is that a self-aligned contact. The reason why we use the SAC process is that when we make the contact plug in here, we should we have to litho and etch another layers, so there can be a misalignment issues or pitch workings. So there can be the difference between the pitch size or the critical dimensions. So for the SAC process, after we make the dummy gate and etch down the dummy gate and grow the high K metal gate, and then we etch this some part of the gate and the etch down the some part of gate and fill the edge stoppers like in blue colors, and then for the defect part on the not conformly metal gate, we etch down the contacts to prevent the killer contact defects. However, it has also very important problems is that the thickness between the metal and the spacers are not even, so it can cause this total capacitance increased. So there is a parasitic capacitance between the metal lines of two lines, and then between the substrate and between the interlayers depositions. So to prevent this parasitic capacitance is that we also electrically isolate with the low K materials like airs, each lines, except for via. It is very important for electrically isolating. So like airs, we say lower epsilons here because it's low K dielectrics. Like so when we deposit, we can use these bad conformities as for the low K dielectric to prevent the electrical interference between the metal lines. Uh, metal lines. The low K materials is airs for the general ways.